I'm Preece. I'm an academic at the University of Manchester, and I work on the Supergen Energy Networks Hub, particularly focusing on work on risk and resilience of power systems. So my research is all about making sure that power systems are resilient, and a big part of that is making sure that they can cope with the different changes that the power system is seeing. So a big driver for that is net zero carbon. We want to make sure that we take out as much carbon from the atmosphere as we put in. And that's meaning that we're shifting a lot of our energy sources over to things like renewable energy, using things like wind and solar, and trying to stop using fossil fuels like gas or coal. And we pretty much stopped using coal already, actually. Now that's causing some challenges. That means that with these different types of energy sources behave in different ways. We're moving from having a small number of very controllable sources, like a gas plant, to having large numbers of uncontrolled sources. So large numbers of wind farms, large numbers of solar plants. That makes it harder for us to maintain that balance in the system. And at the same time, we're also trying to electrify lots of our different kind of energy uses in the system. So things like heating, things like transportation, traditionally they weren't very electric, but now they're becoming more electric. We're seeing more and more electric vehicles on the system. We're starting to see more things like heat pumps as we start to electrify our heating. All of that is adding a significant amount of additional demand onto the network. So at the same time, we've got these two changes happening. We're shifting the type of generation we have over to these more uncontrollable sources, and we're also trying to get more and more power through the network at the same time. So dealing with those two challenges at once is tricky, and that's what my research tends to focus on. So a specific example of some research would be looking at something called cascading failures in power systems. And that's something that I'm looking at in Supergen and working with other people on. So a cascading failure is when we have one problem in the network and that then causes another problem somewhere else. And those problems start to cascade like dominoes, and that can spread throughout the system and potentially lead to a widespread blackout in the whole system. So what I'm trying to investigate is how we can quantify that, how we can work out which parts of the network might be vulnerable, how that risk changes when we have different types of generation in the system, or when we increase the amount of renewables. Does that make things better or worse? How does that affect things? And doing that involves an awful lot of modeling, a lot of analysis, some fairly complex mathematics as well at times. But the idea is that we'll then be able to quantify those risks in the system, and then work out where to try and focus our efforts in terms of trying to solve the problems to make sure that the power system can really cope with these changes and is resilient to different kinds of shocks that it might see. So that might be things like extreme weather, bad storms, extreme heat. All of these things can stress the network in different ways. And so, so the research is really trying to focus in on how to stop those impacts on the network, causing widespread disruption for different electricity customers. So another aspect of my research is looking at the stability of power systems. When we had a large number of gas and coal and nuclear power plants, those are all big lumps of metal that are spinning around. And all that energy that's stored in those big spinning machines, that gives us a safety net if there's ever a disturbance in the system. And it means that we can use that energy that's stored spinning to help cover any losses that we might have. Now, as we change over and shift towards having renewables, to having solar, there's a lot less energy. There's nothing spinning on a solar panel, so there's no energy there that we can tap into. And that means that we have to respond much, much faster to any disturbances in the system. And we also need to be able to control things much quicker. So another part of my research is about looking at what kinds of controls we can use, what's the best way of dealing with that, how do we transition from having large numbers of spinning machines to small numbers, dealing with this low inertia system, as we call it. How do we control that? How do we keep it stable? And how, again, does that make sure that the lights stay on and that we don't see blackouts in the network? So an example of why this is important, we can look to August 2019, when there was a partial blackout for some people in the UK. That was caused by the control of a wind farm behaving in an unexpected way to some things that happened in the network. It decided to back off all of its power and reduce its power output to almost zero, and then that had really bad consequences because that coincided with another failure in the system. So those things happening together at the same time, that then caused a series of events which resulted in hundreds of thousands, maybe even millions of people losing their electricity supply for a short period of time. Now, that's the kind of thing that we don't want to happen. Those kinds of interactions between new types of equipment, where we've got these new bits of kit and they're all being integrated very quickly onto the system. We're not 100% sure how they're all going to behave with each other. And that's why we need this research to design robust types of control that are able to cope with a wide range of conditions so that those types of problems don't happen again. So this kind of research helps obviously electricity customers at the end of the day, because they should end up with a power system that is more resilient and which should experience fewer blackouts and should stay operational. It should also help deliver that more resilient power system at a slightly cheaper cost, because we can target where we make the investments so they have the best value for money. So that's also helping to save the customer money. It also helps us transition to those more uncertain, variable, volatile energy sources like renewables, like wind power, faster, so we can end up with a more sustainable energy system more quickly. And so really by addressing this, we can help drive forward that decarbonisation and try and drive forward making the electricity system greener, more reliable, and also cheaper as fast as possible. As well as that, we obviously work with Supergen partners, people like National Grid Electricity Transmission, or with NESO, the National Energy System Operator. These are people who are obviously very interested in making sure that the system stays operational, and also that their assets, their equipment that's out on the system is well protected and doesn't experience any large kind of damage or faults or bad conditions that can cause issues out on the network. So in the future, we're going to have a power system which has all these new technologies, all these new types of generation installed. It's also going to have all these new types of electrical load, lots of electric vehicles. We're going to be reliant on that system a lot more, because a lot more of our energy is going to be coming to us through the electrical network. So it's really important that it works and that it delivers on those affordability, that sustainability, and that reliability. Now, obviously, my research is a part of that, but through Supergen, we're also working on all sorts of other aspects which will also help feed into that. So it's not just about risk and resilience, it's also about the digital infrastructure, making sure we've got the right data so that we can control those new types of generation. It's about having the markets and the regulation processes in place to make sure that that we're delivering affordable energy and that we're able to keep that system operational. And it's also about having the kind of good understanding of the societal impacts of all of this, because at the end of the day, we don't just want to have the electrical network operating because we want the electrical network operating. We want it because we want the service it provides us as people. We want that energy so that we can do other things in our life. Most of us aren't really concerned about just having energy for the sake of it. We want energy for transportation. We want energy for heating, for cooking. It's all the other benefits it brings us. And so that's why Supergen is looking at all those different aspects and trying to bring them all together in one project so that we can really focus on getting the most out of our energy systems of the future and making sure that the energy system itself can really help drive forward that decarbonisation.